good, y'all? It's your boy Jesky Chuck back with another creepy and scary TikTok that might just shift your paradigm. And I just want to say, if you haven't already, click that like and subscribe button. And if you're new around here, uppercut that bell and set that notification to all. Today, we on Quantum Waters 9. That's right, we're going to be diving back into these quantum waters. We're going to be diving into this tesseract. We're going to be diving into string theory. Yeah, that's right. I'm interested in this quantum, and it's just been a huge subject in the past. Always been something I wanted to dive in more on, and I'm excited to dive into it on today's episode. So without further ado, let's jump into these quantum waters. Ayusan! You know, looking at this kind of reminded me of Interstellar. Have you guys seen that movie? That's one of my favorite movies of all time, Interstellar. And tell me that's not the inside of it. It looks just like that. Let's dive in a little more.
Representations of the fourth dimension. What does the fourth dimension look like? Christopher Nolan's Interstellar has one of the best movie representations of the fourth dimension. One simple way to attempt this is to see what happens when you mathematically render a square into the fourth dimension. A square is a two-dimensional shape. In the third dimension, you get a cube. And in the fourth dimension, you get a tesseract.
You mean like this?
No. This is the closest representation we have to a tesseract. Now, we cannot comprehend or even imagine what a real tesseract looks like because we are three-dimensional beings, but our eyes perceive things two-dimensional. Theoretically, there is a fifth and sixth dimension and so on. So for now, we can only wonder, what does the fourth dimension look like? Christopher Nolan's Interstellar has one of the best movie representations of the fourth dimension. One simple way
Welcome to the fourth dimension. Welcome to the fourth dimension.
No, not yet. But one day. Not you and me.
Time is relative, okay? It can stretch and it can squeeze, but it can't run backwards. Just can't. The only thing that can move across dimensions like time is gravity on that planet will
Is
slow
love.
our clock compared to Earth's drastically.
I bet.
Well, every hour we spend on that planet will be 7 years back on Earth.
Imagine that this folder is a dimensional plane. Now, assuming that it is no height and no depth, what would this mean? It would mean that it's a one-dimensional world. So if, hypothetically, an organism was living inside of it, it would only be able to move in a linear path forward and backwards in a straight line. Now, if we go to the second dimension, we have two dimensions. We have width and we have length. So hypothetically, if an organism lived inside of here, then it would be able to move up, down, left, right, and anywhere else in between. upon a circle, the light would make it appear to be lighter at one end and darker in the middle. Also, imagine that this connects piece represents the first dimension. It's simply a straight line, which is basically what the first dimension looks like. And if you add 3 more of these straight lines and connect them so that adjacent sides are perpendicular and opposite sides are parallel, then you have the basic shape of the second dimension. You have a square. Now if you keep going from here and you add it so that there's a total of 4 squares, and all adjacent sides are perpendicular and all opposite sides are parallel, then you end up with, obviously, a cube. So if you tried to keep going from here, and you would have a 4-dimensional basic shape, you would have what's called a tesseract. Now I cannot show.
Boy, the pieces are starting to add up. The tesseract, man, he was on something. How long ago was this? Where's the tesseract now? Who's the first person that ever said tesseract? I want to know.
Show you a tesseract, but you need to understand that it's basically 4 cubes that are within each other that have all adjacent sides perpendicular and all
Hold on, where have I heard a cube before? Don't tell me Saturn. Oh no, don't tell me the tesseract is on Saturn.
opposite sides parallel, yet there are 4 lines connecting to each vertex. So a tesseract would look somewhat like this picture. Now that's not exactly what it looks like, because this is a 2-dimensional depiction, and obviously not all of the lines are straight. So I cannot show you what a tesseract actually looks like, because we cannot perceive things in the 3rd dimension. You can't.
Okay, this is going to sound a little nuts, but the fastest and easiest way to make passive online on Amazon is to
Now, dimension, or go to the 5th dimension. The 6th tesseract looks like. You cannot in your mind picture the 4th dimension or a 4th dimensional shape. And you can keep going on from the 4th dimension even. You can go to the 5th dimension, the 6th dimension, the 71st dimension. It doesn't matter. Theoretically, there are an infinite amount of spatial dimensions. Make any sense.
We cannot see all ends. Trust me. The smartest and the wisest cannot see all ends. But what we can say is a quantum entanglement did happen. Some call it the Big Bang. Some call it Genesis 1. However you want to stir it or however you want to spin it, something outside happened. And whenever you're thinking about time, time is the sun and moon rotating. As long as the sun and moon rotates, that is time. So that it makes perfect sense because quantum entanglement happened. An outside source from a different dimension did a quantum entanglement. Through a certain frequency created everything. That's what happened, a quantum entanglement. And as far as time goes, time is the sun and moon. As long as the sun and moon move, that is time. Time doesn't affect the 4th dimension. 1 hour of our time of the sun and moon rotating could be 1,000 years. He says it doesn't make sense. This was already written thousands of years ago of how time is affected in the 4th dimension. Let's look it up. Look at 2 Peter 3:8. If we look at 2 Peter chapter 3 verse 8. Second Peter verse 8. Man, 2 Peter short. 2 Peter verse 8. Kepha bet. It's chapter 3 verse 8. It says, but beloved ones, let not this one matter be hidden from you, that with Yahuwah 1 day is 1,000 years, and 1,000 years is 1 day. That's what it say. I'm gonna take a picture and throw it up there for y'all so y'all can see it. But it's really not that big of a mystery if you lean not on your own understanding.
They returned to Earth. They would find that Earth had actually progressed a few years, so they had moved forward in time by moving that quickly. Another interesting concept involving the fourth dimension is that many physicists and even mathematicians say that nothing can be truly infinite, but if this is true, and a dimension is really within another dimension, within another dimension, within another dimension, then I'm implying that there's an infinite amount of dimensions, which is the only problem I really have with this theory. I'm not sure if it ever stops, or if infinity is really even possible. We don't know that.
Imagine I have a beautiful tree that's filled with oranges. And I ask myself, what is the orange made of? How do I answer that question? Well, I want to look deeply inside the orange, so I magnify it. And I magnify it again, and if I keep on doing it, deep inside, sooner or later, I begin to see molecules come into view. But molecules are not the end of the story, because the molecules, I can enlarge them. And if I make them big enough deep inside, I begin to see atoms. Atoms are not the end of the story, too, because we have electrons zooming around the nucleus. Deep inside, mostly empty space in the atom, but deep inside, we see the nucleus. So if I grab that and magnify it, I see that the nucleus is itself made of particles, neutrons and protons. And if I grab one of the neutrons and magnify it, I find yet further particles, little tiny quarks inside. Now that is where the conventional ideas stop. String theory comes along and suggests that inside these particles there is something else. So if I take a little quark and I magnify it, conventional idea says there's nothing inside, but string theory says I'll find a little tiny filament, a little filament of energy, a little string-like filament. And just like the string on a violin, I pluck it and it vibrates, creates a little musical note that I can hear. The little strings in string theory, when they vibrate, they don't produce musical notes, they produce the particles themselves. So a quark is nothing but a string vibrating in one pattern. An electron is nothing but a string vibrating in a different pattern. A neutrino, nothing but a string vibrating in a different pattern still. So if I take all of this back together, I have my ordinary orange, and if these ideas are right, they are speculative, but if they are right, deep inside the orange or any other piece of matter is nothing but a dancing, vibrating cosmic symphony of strings. That's the basic idea of string theory.
What string theory is?
Sure. The basic idea is pretty simple. If you take any object, for instance, the tabletop, and magnify it and examine it on very small scales, there'll be molecules and atoms. And if you look at the atoms and magnify them, you'll see that there's a nucleus, protons and neutrons, surrounded by orbiting electrons. And in 1968, we learned that if you magnify a proton, there's yet further substructure. The Russian dolls continue. Inside there are 3 quarks, even smaller particles. Now, for a long time, people thought quarks and electrons were all there was, together with a few other exotic particles that make up the universe. String theory comes along and says, actually, there's one more level of substructure. If you examine an electron or examine a quark at incredibly fine resolution, you'll find that there's a single loop of vibrating energy that we call a string. And that's the idea of string theory, that all of the particles in the universe are different ways in which a fundamental loop of energy can vibrate. So much like a violin string can play a C, it can play an A sharp, different notes that our ear senses, different tones, the different ways that these fundamental strings vibrate correspond to the different particles of nature. An electron is like a C, a quark is like an A sharp, and so forth.
We know that there are these 4 dimensions. We know that there's height, we know there's width, we know there is length, and we know there's time, right?
That's right.
There's the 4.
Right.
String theory brings 6 new dimensions.
Yeah, at least 6.
At least 6.
Maybe 7.
Maybe, okay. What are they?
Well, they're actually of a similar character to the ones that we're familiar with. They're just very tiny. And actually, I have a small prop that I like to use
I love show and tell.
to describe this. So forget about the universe for a moment, and let's just look at this piece of wire. Now, from very far away, this wire would look like it's one-dimensional. In that, for instance, if a little ant was living on it, you'd say, well, it can move left and right along the wire, but that's it. There's only one possibility. But then as you get closer to the wire, you realize that there's a second curled up circular dimension, the circular girth of the wire. And therefore our microscopic ant can not only go back and forth, it can also walk around the wire, a second curled up dimension. And what this little example alerts us to is that dimensions come in two varieties. They can be obvious and long and easy to see, or they can be tiny and curled up and more difficult to detect, like the circular girth of the wire. Now, what the idea is, according to string theory, is that the fabric of the universe is much like this piece of wire, in that there are the familiar dimensions that you referred to, left, right, back, forth, up and down, and also time, but there can be additional dimensions that are tightly curled up like the circular girth of the wire and are so small that we haven't seen them yet because we don't have sufficient magnifying instruments to actually peer down into the nooks and crannies of the spatial fabric and see these extra dimensions. But string theory says that they absolutely have to be there. There are at least 6, as you mentioned, and quite possibly 7 that are curled up into the fabric of the universe.
Is this such a hard idea to tackle that there may be 10 people doing it in the world, or is this something that there is every young physicist on every campus in America thinks that I'm going to find the answer to the riddle of unity in nature?
It's more like the latter. These ideas seem abstract at first, but when you do phrase them in the language of mathematics, you find that it's actually not that difficult to describe all these extra dimensions. And graduate students across the country are learning about string theory and doing research, some of it cutting-edge research on the theory.
How do you go about the investigation? Now, can I imagine you sitting in front of a computer doing thousands and thousands and thousands of equations?
That's close to it. Certain projects do require a computer to do the analysis. Other times it's really a pen and paper, and it's just manipulating symbols which describe these extra dimensions or which describe the strings.
Looking for what?
Well, what we're looking for is a coherence in the equations which will show us that we actually have a theory that is, number one, self-consistent, and number two, actually describes our world. It could be that you come upon a wonderful theory that describes gravity and quantum mechanics and all the things around us, but it misses. It's a near miss.
Right.
For instance, it might predict that the electron weighs 10 times what it actually does. If that's the case, you have to throw the theory out the window. That's right. So what a lot of us are doing is trying to extract observable physics from this theory and compare it with experiment. That's the goal, and we're a bit far from it, but that's what we're trying to do.
What a bummer would it be if you think you found it, and it tests well here, tests well here, tests well here, tests well, and then you get to like your 999th test to see if it fits.
Well, that's science.
It doesn't fit.
Yeah, it would be quite a bummer. It'd be a real drag, but that's sort of what science is about. You know, you get.
Yeah, man, that's what science is about. You just gotta do your best, you know. But
so there's a scientific theory that says everything is made from vibrations, and when you think of vibration, you think of sound, right? Basically, there's so many different frequencies of sounds. For example, steel would be one vibration frequency, wood would be another vibration frequency of sound, and in the beginning of the Bible, in Genesis, it says, "And God said, and it was so." And when you think about that, everything around you is upheld by the Word of God. If you're sitting at your kitchen table eating dinner, you're sitting literally on the Word of God. If you're driving in your car, you're literally driving inside the Word of God. So God is literally everywhere around you. When you break down the word universe, it also references the Bible. So uni is one, and verse, you know, God spoke the universe into existence. He's absolutely correct.
For a long time, cosmologists and others believed that our universe was eternal. It was always here, and they opposed and fought the growing evidence that our universe actually had a beginning, opposed it due to its obvious theistic implications. A beginning to the universe? We can't have that. That sounds like creation. That sounds like God. But now they all believe that the Big Bang was the beginning of our universe. So there was eternal nothing, no space, no time, no matter, no energy, no laws of physics, no nothing, and then all of a sudden, literally out of nothing, there was a quantum fluctuation. Ha! Talk about pulling a rabbit out of a hat. Talk about a desperate deus ex machina, a quantum fluctuation, a fluctuation in nothingness, and the universe, space, time, matter, energy, the laws of physics, they just appeared out of nothing. Nobody can explain the origin of the Big Bang. Nobody has any idea how it occurred. Nobody, that is, but the theologians. Genesis 1:1, in the beginning, God created the heavens and the earth.
that man was fitting. How you saying?
If you're saying nothing created everything, then you're agreeing with Richard Dawkins.
Characterizing Richard Dawkins, because Richard Dawkins, I'm sure he didn't say that. That seems ridiculous.
Professor Richard Dawkins, arguably the world's most high-profile atheist, believes that in the beginning there was nothing, and that nothing created everything. As he attempts to justify this belief, admitting that it defies common sense, the learned professor calls nothing something. Watch the reaction of his audience.
Of course it's counterintuitive that you can get something from nothing. Of course common sense doesn't allow you to get something from nothing. That's why it's interesting. It's got to be interesting in order to give rise to the universe at all. Something pretty mysterious had to give rise to the origin of the universe. It's exactly what's meant by nothing, but whatever it is, it's very, very simple. And why is that funny?
Well, I think it's a bit funny to be trying to define nothing.
Richard Dawkins, I'm sure he didn't say that. That seems ridiculous.
If you're saying nothing.
That's it for today's episode, y'all. If y'all made it this far, drop the 100s in the comments so I know you real, man. We was on quantum waters today, and I appreciate y'all, man. If you haven't already, hit that like and subscribe button. We do this daily. And uppercut that bell and set notifications to all so I know you real. As soon as I upload these boys, drop the like on the video and comment, Jesky Chuck, we in here. Notification gang, I see you. We on these waters together. I'm not on this by myself. I got y'all right beside me. That's what's up, man. I love y'all talk, man. Until the next episode, I'ma holler at y'all. Be safe out here. Peace.